Numerical Computation, Chapter 6, additional video number 4. This video can be viewed after you have finished the additional video number 3. We study singular value decomposition in this video, known as SVD. We first define a couple of concepts. So given a matrix A, we denote by A to the H, the conjugate transpose of A. This means we consider the case A with the complex numbers as the entrance. A square matrix A now is called unitary if AH times A equals A times AH equals identity. A unitary matrix is also called an orthogonal matrix, where the column vectors in A form an orthogonal set. And we have AH equals A inverse. Now, given a matrix A, not necessarily a square one, but with full rank, then the product AH times A is symmetric and positive definite. That implies that the eigenvalues lambda I of this matrix, they will be all real and positive. And these are the values that one used to form something called the singular value. So we define sigma I to be the square root of the eigenvalue of this matrix AH times A. Since these are all real and positive, the square root will return a real and positive number, and for each I from 1 to n. And these sigma i's are called the singular values of A. So you are expecting that our decomposition would utilize those singular values. Here is the singular value decomposition statement. So given a complex value matrix A with the m bigger than n, then there exist two unitary matrices, U and V. U is a square one with size m times m, and V has size n times n. And we have a diagonal matrix, we call it D, which is m times n. So this D is a rectangular shape, the same size as A. And then A can be written as U times D times VH. Here, the diagonal matrix D would exactly contain the singular values on its diagonal. One can reorder the singular values such that sigma 1 is the largest and sigma 2 is the second, and it decreases, and sigma n is the smallest one. Now this is called the singular value decomposition. In the special case where A is a real matrix, both U and V are real and orthogonal matrices. Once the singular value decomposition is given, we can use it to solve the system AX star equals B. Here are some details. We start with the A matrix, which is U, D, VT, the singular value decomposition. Then we compute the A transpose, which is the transpose of each of them, but reversing the order. Then V transpose give you V, and then you get D transpose and V transpose. And using that, I can compute the matrix A transpose A. That will be a square matrix. So this is A transpose, and that is A. Removing the bracket, using the fact that U is unitary, so UT times U is identity, this we can drop, and we have V dt d vt. Hence, AX star equal B now is equivalent to A transpose A, X star equal A transpose B. And we have just computed the expression for A transpose A. Then we can plug that in, which was this one. We plug it in over here. And for the right-hand side, we put A transpose, the expression here, over here, and multiply by B. We now further manipulate this equation. We multiply on the left of both sides of the equation with this expression here, that is V dtd, the whole thing inverse, times Vt. And you see that if you multiply this on to the left of the left-hand side, and you will have V times Vt in between, and that is the identity matrix. And then on the left, we would have dtd inverse times dtd, and that gives you again identity matrix. And finally, you would have an V times the Vt, that again gives you identity matrix. So basically, this thing here is the inverse of what stands in front of X star. And now we would have X star equals this expression here times the right-hand side. And then again, we use the fact that Vt times V is identity, so we remove that term in the middle, and this is what we get. We see what we have here is this whole expression here in the end gives me a matrix times B. So let me call that matrix A star. A star is exactly this expression. So we can consider this A star as some kind of an inverse of A, but not in a regular sense, because A is not a square matrix. So this is called the pseudo-inverse. We remark that a symmetric version of the decomposition exists for the case where m is less than n. The SVD is available as a Matlab function. For example, you have SVD, you send in a matrix and you can receive it in the three matrices U, D, and V. There is another function called SVDS, also gives you singular value decomposition. I encourage you to use the tutorial of Matlab and see more detailed options for these functions. So here the singular values will be stored in this diagonal matrix D in decreasing order of their values. So beyond solving an overdetermined system, the singular value decomposition is very popular in the application of image compression. So we'll go through the details here and take an example. Let's consider a very large matrix, which represents a rectangular image. Each element in A indicates the color intensity of the image at that position. So if your image is a grayscale image, then you get a single value. Otherwise, if you have a colored image, then this will be a vector of 3, depending on what format you use to define the color. Usually it takes 3 components. We take example of a grayscale image. Then A is a matrix of size m times n, possibly m and are both very large. Assume that the SVD decomposition is given for A. So A equals U times D times VH. We now pick a parameter, we call it K, which is an integer, and typically it should be much smaller than both M and N. And then we form some submatrices. We form a matrix UK, which is M times K, and we form a matrix VK, which is size N times K. These are rectangle matrices formed by taking the first K columns of the matrices U and W respectively. Okay, so they can be a skinny rectangle shape, that the UK and the VK matrices. And then I form a diagonal matrix DK, which is a K times K matrix. And this one I would take only the first K diagonals of D. So utilizing these submatrices, we can form a sequence of matrices. We call it AK, where K can change. So AK would be UK times DK times VKH. So this is in the same order as the singular value decomposition, but now we use the submatrices. And we see now if the K number gets bigger and bigger, especially when K equals M, then we would just have U and K and V here, and then the A matrix, AK or AM, will exactly equal A. Now, one amazing fact is that this convergence, as K increases to M and a K matrix approaches A, that convergence is very fast as K grows. So AK approaches A extremely fast when K grows. This means with a relatively smaller K, much smaller than M or N, one has an extremely accurate approximation AK for the matrix A. Therefore, one can store the informations for AK instead and save a lot of memory space. And this is called image compression. To store the AK matrix, one would store the matrices UK and VK and the diagonal matrix DK, which one only needs to store the diagonal elements. Next, we take an example. The iconic image used in this application is a photo of the supermodel Lena. If you Google it, it's everywhere online. And here we take a different image. I say equally adorable. It could be a subjective judgment. And this is an image of one of my cats. So this image is stored in the file named kitty.jpg. And I wrote this Matlab script and basically using the SVD to decompress my image. Okay, so let's go through the script and see what it does. So the first line, image read, it's to read the file kitty.jpg and install it in K. and then I take one color component and store it in A, and now A will be a matrix. So here the image kitty.jpg is almost a square image, and the A matrix here is approximately 640 times 640, the size of it. And in Matlab, you can display the image of a matrix by the command image and sending the matrix. So we generate a new figure and we display it, and we define the color map to be gray, so we'll see a gray image of the cat, and make the axis equal. And now we do the single value decomposition. So we take the double A, set it to A. What it does is that it changes the data type of A to double. So Matlab can use those numbers and perform a singular value decomposition of A, and we store them in U, D, and V. And now we form the submatrices. We take K to be 20, which is much smaller than 640. So we'll be using only the first 20 singular values. And we form the submatrix. U20 will be taking the first 1 to 20 columns of U, and D20 will be taking the first K diagonal elements of D, and the V20 will be again taking only the first 20 columns of V. And then the A20, this AK matrix, is formed by this product, U20 times D20 times V20 transpose. This is to form an approximation to the A matrix. And then we open another figure and display this image. So in order to display image, you need to change the data type into an uint8. It's just a Matlab standard format for image display. Okay, and you define the same color map to be gray and set the axis to be equal. And then this whole thing is repeated again after I set K to be 60, and then we go through the same thing, form the submatrix, form the A60, and display it. So in the end, I would get 3 images. One from here is the original kitty JPEG image, and then here is using only 20 singular values, and then the third one is an image that utilizes only 60 singular values, and as against the size of the image will be 640 times 640 approximately. So here is the output of the program. On the left, what is shown is the original picture of the cute kitty, and the middle one is generated by A20, where K equals 20. We use 20 singular values, and you see it's a rather poor image. It's very much blurred, but you can still distinguish a cat there. And then the third one, the one on the right here, is when K equals 60. And we see that's amazingly similar to the original image that we start with. Now, to get a concrete idea of how much space we would be saving by taking only 60 of the singular values, we can do a simple computation. So to store the original image, so the original image is actually 638 times 640. This gives us about 408K numbers to store. And then to store the one on the right, we just need to store U60, D60, and V60. And we do a product and we immediately recover the A. 60. So U60, the size is 638 times 60. And for the diagonal one, we just need to remember the first 60 singular values. And for V60 will be 640 times 60. If you add this up, what you get is 76k numbers to store. So you see this is much smaller than that, and you save a lot of memory space, and yet you still have an amazingly good approximation to the original image. Okay, that's all for this video. Hope you enjoyed it, and thanks for watching, and see you next time.